Hello everyone. In this lecture, we will talk about convolutional neural network. This lecture is primarily based on two materials: Sherwin CNN cheat sheet for CS230 in Stanford, Sherman's CNN tutorial below. Why do we talk about CNN? Let's look at the examples of physics data, popularly as the image processing problem. In particle physics, we ask the questions how to identify top quark from a QCD jet. These two images, one represents the top quark, the other represents typical QCD jet. We will talk a bit more detail about how this data are preprocessed, and we will work on the in-class quiz and the lab questions based on this jet image data. In the astronomy side, here you can see a couple of different radio galaxies. The research in this field is to identify different images represent different types of galaxies. The cutting-edge development of the image processing is computer vision problem. The big challenge in computer vision is how can we classify an object when input data get really big. For example, this is a picture of a bird. When we look at this picture in digital data format, we can describe this image based on pixelated data. If we have an image size of 32 pixels, it means in the height and the width, each has 32 pixels. We have three colors, red, green, blue. Each color we can describe in a number from 0 to 255. With a combination of these three colors, we are able to build the full colorful picture in the digital world. In the pixel size of 32, the input element is 32 by 32 by 3. That is 3072 pixels. We can treat it as the input of the neural network. We can build a classifier using fully connected network. Try to classify this image as a bird, as sunset, a dog, a cat, or vice versa. This is a multi-classification problem. However, this can become a really difficult problem. The input size is n. In the next layer, the number of neurons is m. The number of tunable parameters is n plus 1. So 1 is the bias introduced to the hidden layer times m. This will represent the total connection between neurons. The number of weight here is already reached 9.4 million. We are even not talking about more complicated case. That is, add more intermediate layers yet. The idea of the convolutional network is to define filters which can detect key features of the image. We can apply the same filter multiple times on the images, then we can reduce the dimensionality. A convolutional network is mostly composed of convolution and pooling layers and followed with fully connected layers. The function of the convolution pooling layer is to reduce the dimensions. The fully connected layers classify the reduced dimension data into multi-classifications. In this lecture, we want to learn how to calculate the tensor size at each stage and how to calculate the total number of parameters in the network. Let's have a quick overview about each of the components. In the convolutional layer, it uses filters to perform convolution operations as it is scanning the input data with respect to its dimensions. The parameters of a convolution layer include the filter size, the padding, and the stride. Here is one cartoon showing an example. We have an image of 6 by 6 pixels, and we have a filter 3 by 3. The filter will be applied to the images, and this 3 by 3 filter applied to the first 3 by 3 pixels of the images. It computes into one number, filling into output images. The same filter will be applied to the next 3 by 3 pixels. The result will be filled into the second element of the output image. We continue to shift the filter applied to the image. Eventually, we have a reduced size of the image. The pooling layer is a down-sampling operation, typically applied after a convolution layer, which does some spatial invariance. The parameter of the pooling is the filter size and also the stripe. We have two popular types of the pooling. One is called the max pooling. Take one example. We have a 2 by 2 max pooling. We apply to the first 4 pixels. In these 4 pixels, we will choose the maximum value and fill into the output image. For average pooling, instead of finding the maximum value, we will take this 4 pixel, calculate the average value, and fill into the output image. We shift the filter based on the stripe. That is the window size. We shift the filter. With this, you can go through the 4 pixel and reduce the image size. Once you apply the convolution layers and pooling layers, you have a reduced image size. The reduced image size can be flattened, reshaped into one-dimension vector. With this one-dimension vector, we can build multi-layers of the fully recounted network, and the output layer can be multi-classifier. This can significantly reduce the complexity problem. Now, let's try to walk through each of component in detail. First, let's start with convolution and nonlinearity. A convolution filter have 3 key elements. First is the image input. We apply a filter or kernel. The output image, we call it feature map or activation map, or the output. This activation map is the output of this image. We can pass into activation layer. How to calculate the feature map size? We can describe input size I is I by I image and apply a filter with the size f. The output size O depends on the formula I minus f plus 1. Let's take one example to walk through the algebra. Here we have a 6 by 6 image. We will apply to a filter. This edge filter have 1 in the most left column, 0 in the central column, and -1 in the right column. After applying the filter, we will apply this filter on this image and shift this filter to the full image. With the stripe 1, the output image size, find the formula, it will be I minus 1 plus 1, I is 6, F is 3, therefore you calculate output is 4. We expect a 4 by 4 output image. Let's walk through this algebra in detail. To calculate the first element of the feature map, we apply the filter in the first 3 pixels. And the way to apply this filter is each element times the filter in the corresponding element position. And in this case, it's 1 by 1, 2 by 0, 3 by minus 1, 2 by 1, 2 by 0, and 5 by minus 1. Then we add all these numbers together to get a minus 14 and fill into the feature map. This sliding window will be shifted to the second element. Again, we apply the case that 2 times 1 plus 3 times 0 plus 1 minus 1. And once we add up all these 9 elements together, we get minus 1, which will be the second element in the feature map. The next sliding window, we do the same calculations, multiply the 3 by 3 image to the filter element, and add all the elements together, we got 10. Then we shift to the fourth element here. And once we finish this calculation, we cannot shift to the right-hand side anymore. In that case, we'll jump into the second row. And this second row will fill in the second row of the feature map. We can continue to go through this process. And eventually, we have a 16 element. This will give us a 4x4 output feature map. Therefore, we start from a 6x6 input image, apply a 3x3 filter, and we get a 4x4 output feature map. There are several famous filters. A 3x3 filter with all elements 0 except center is 1. This is an identity filter. The image applied on this identity filter, we get the original image. Because the padding is 0, therefore, the output image pixel will be less than original image. And if we apply a sharpen filter, the center have a higher value than the neighborhood, and this can sharpen the image as the output shown in the right-hand side. And on the other hand, if we have a large value in the center and we have negative value in the nearby image, we can get an image with identification of the age of the object. If we have a filter have a larger value in the center, smaller value in the neighborhood, and even smaller value in the offside corner, this is so-called Gaussian blurring, make the image look softer. The other parameter for the filter is called padding. You can expand the input image by adding 0, and with this way, you can increase the output image size. When the padding size is p, that means you will grow additional length in both sides. Therefore, the input size of the image is increased to I plus 2p times I plus 2p. Once you apply a filter with the size f, the output image size will be I plus 2p minus f plus 1. With this formula, we can observe a special choice of p, which is f minus 1 over 2, can give us the output image equal size as the input image. Let's take one padding example. This matrix with padding 1, we will grow the width and height with 1 additional pixel with a value 0. Now we apply the filter. The first element of the output image will be centered here. Once you calculate this matrix, you get minus 4. So the output image, it will become 6 by 6 instead of 4 by 4. And this 6 by 6 output image is the same size as the input image. If we apply the formula, we can verify I plus 2p minus f plus 1, I is 6, p is 1, and f is 3. Therefore, you get output size 6, which is consistent with our operation. The stride denotes the number of pixels by which the window moves after each operation. All the example we have shown so far is stride 1. If we put stride 2, the next sliding window will shift by 2 pixels. And after we finish operation, the next sliding window shifts another 2 pixel size. With this feature, we can calculate the expected output size. The input size is I, and the filter size is f. The output size will be I minus f plus 2p divided by stride size plus 1. This could be a non-integer value. That is, drop the decimal point and keep the integer number. We can review the example. If we apply stride equal to 1, we will get the output image 4 by 4. How about stride 2? In the stride tool, when you shift the sliding window, after the first shift, you can calculate the two element value, but in the next shift, you need to shift 2, and you will go beyond the input image size, and we will stop here. Therefore, you only have a 2x2 image output. If we apply the formula, the output size is a floor of I minus f plus 2p divided by s plus 1. I is 6 in this case. Filter size is 3, and we are padding this with 0. Therefore, we get a floor of 2.5. We'll drop the decimal point, and the answer is 2, which is consistent with our operation. Of course, we can talk about the image with more channels. As we show in the beginning, to describe a colorful picture, you need 3 channels, red, green, blue. In this case, our image not just have a height and width, but also have the depth. The volume of the image is I by C. C is the channel number. The filter need to have the same dimension of the depth as the input image. If we have a channel number C as the input image, the filter also need a channel number C in the depth. The output will be just one layer because we will apply the filter to each channel. Each filter applied to each channel will get to one number, and each channel get one number, we will add them up all together, and eventually we'll only fill into one channel array. We could have a multiple filter, and each of the filter have f by c volume. And in this case, each of the filter will generate a channel output, and we can add a bias of every single number with a constant. Then the output of volume of the image will be O by O by K. K is the number of a filter. Up to now, we can see the benefit of using the filter because we apply the same filter, scan through all the images. Therefore, the free parameter, that is the tunable parameter for the machine learning train, will be based on the number of elements in the filter. So each filter have a f by c number of the parameter, and with additional bias, then in total we will need multiply this with k, which is the total number of filter. Let's take one convolution layer as an example. We have a 32 by 32 pixels with 3 channels. There are 2 filters. In each filter is a size of 3. So you have a 3 by 3 by 3 channels. If we calculate the output size, it should follow the formula I minus f plus 1 because the padding is 0. Therefore, the output size is 30 by 30. And once you get the output image, don't forget to add the bias term to all the number. And each of the filter will create an output image there. So the volume of the output image will be 30 by 30 by 2. 2 is the number of filters. What's the hyperparameters of this case? It will be 3 by 3 by 3 plus 1 for each of the filter by 2. That's the total filter number. Therefore, we have a total number of the 56 hyperparameters. Take a numerical value of this particular case. So we have a 6 by 6 pixel by 3 channels, and we have 2 filters. The first filter is a 3 by 3 by 3 channels. The second filter is also 3 by 3 by 3 channels. And each filter after application, we will add a bias term. So we expect to have output volume 3 by 3 by 2. This 2 because of the number of filters. How do we get the output image channel number 1 here? This 2 is calculated by applying filter to each channel on the first 9 element. You will calculate 0 by 1 plus 0 by 0 plus 0 by 1 and vice versa. So once we sum up all those numbers, then we add this bias number 1. And then we will put into the output image 2 over here. Then we can do the sliding window. In this case, our filter have a strike 2. That's why we shift by 2 pixels. And we do the same calculations. We calculate this multiplication and sum them together and plus the bias 1. We get the second number of the output image minus 1. And we continue to shift the filter and all the way through, and eventually we complete the first channel of the output image. Then we can repeat the same calculation for the second filter. In the second filter, the first element will be multiplication of the filter to the first window, sum up all the elements, and plus the bias. We get a minus 2. Then we shift the filter by strike 2, continue the process, and eventually we complete the second channel of the output image. Now let's check the volume size of the image. The input volume will be I by 3 channels. That is 5 by 5 by 3. How about the output size? Output size should follow the formula I plus 2p minus f divided by the stretch size plus 1. I is the input dimension 5, and padding, we have 1 padding, and the filter size is 3, and stride is 2. Therefore, we compute the output size should be 3, as shown here is 3 by 3. And the output volume will be 3 by 3 by number of the filters, 2. What's the hyperparameters of this case? Hyperparameters will be filter volume plus 1 bias times 2 filters. So it's 3 by 3 by 3 and plus 1 multiplied by 2, and that is 56. The hyperparameter we use for the training in this convolution layer will be 56 parameter. How do we introduce this training? By adding a nonlinearity of the model. We usually use the rectified linear unit as the activation for each of the output image element. Of course, there are other popular activation functions. For example, you have sigmoid or tanh. Rectified linear unit have a 0 value when the quantity is below 0, and it is linear after greater than 0. We also have a leaky rectified linear unit, or max out, or ELU. And ELU is interesting. It will guarantee that all the numbers will be differentiable. After introducing the convolution nonlinearity, and we can talk about the pooling. As mentioned earlier, there are 2 major types of the pooling, max pooling or average pooling. We can take a numerical example. Here is a 4 by 4 image, and we have a filter size 2, strike 2. For the max pooling, we will look at the first 2 by 2 element. The maximum value is 9, therefore we fill in 9. For the second window, we have maximum value 2, we fill 2 over here. And we have 6 and 3 in the rest of the 2 windows. Then we finish the downsampling output image. For the average pooling, For each of the window, we calculate the average of all the 4 numbers, and we can get the output of the same size 2 by 2. We can check the formula here. I is 4, f is 2, and stride size set to the same value as f, and we can compute the output of floor is 2 by 2. In most cases, we set the stride length equal to the filter size. There are 0 number parameters for pooling in the training, because in the process here, there's no weight to be tuned. Once we have convolution and pooling layers, we have a downsize of the image. We will flatten the image, put into fully contained network, generate the multi-classifier output. A popular choice of the activation function for the multi-classifier is the softmax. Softmax have a multiple neuron output, and we want to map this multiple neuron output into 0-1 interval. To do so, we define exponential of the score value of each neuron output, and the denominator is the sum of all the exponential of the score output. With this definition, we guarantee that the sum of all the neurons equal to 1. This gives a nice interpretation. The softmax result can be considered as a probability to be identified as a particular classification. Now we can put everything together. Here's one example of the CNN. We have a 2 convolution pooling layer. Then we frame into a 1-dimensional tensor and follow with 2 fully connected hidden layers. And then we have a 1 softmax layer output. What's the benefit of a convolutional neural network? There are 2 major benefits. One is parameter sharing. Filter can be used in different parts of the inputs. Furthermore, from the 4 calculations, we have a sparsity of the connections. In each layer, each output value depends only on a small number of inputs. We have the translation invariance taken into account during the filter operations. Let's try to look at implementation in TensorFlow. So we will create a sequential model. And in this example, we have 3 convolution layers sandwiched with 2 pooling layers. The input shape is a 32 by 32 pixel image size with 3 channels. And we have 32 kernels, and each kernel is a 3 by 3 filter. The activation function for the first convolution layer is a rectilinear unit. We can calculate the expected output size of the first convolution layer. After applying the formula, the padding is 0. Therefore, you can calculate I minus f plus 1 is 32 minus 3 plus 1, which is 30. You can see here the output of the first convolution layer is 30 by 30. This 32 comes from the fact that you have 32 kernels. What's the hyperparameter which is tunable in the first convolution layer? The parameter is filter size times the number of the channel plus bias turn times the number of kernel. So the filter size is 3, channel number is 3, and kernel size is 32. Therefore, we can get 896 hyperparameter for the first convolution layer. And then we will pass this 30 by 30 by 32 as an input to the first max pooling layer. The max pooling layer, the filter size 2, and by default, the stride is the same as the filter size 2. Therefore, we can calculate expected output, I minus f over s, and plus 1. We can calculate expected output of the max pooling layer. It's I minus f over s plus 1. And the input to the max pooling layer is 30, and the filter size is 2, divided by stride size 2, the same as the filter size, plus 1, we get 15. This is the output of the first max pooling layer, 15 by 15, and follow with the kernel size 32. So the tunable parameter for the max pooling layer is 0. by construction, there's no tunable parameters for the pooling. Then we pass this 15 by 15 by 32 as input to the second layer of the convolution network. The second layer convolution network, we have activation function, ILU. The filter size is 3 by 3 with 64 kernels. Then we can calculate the expected output after the second convolution layer. So I minus plus 1, I here is the 15, and filter size is 3. Therefore, we get the output size 13. How about the tunable parameter? Tunable parameter is filter size, which is 3 times the channel. This channel is 32. That is the input channel size. And plus 1 times k. K is the number of the kernels defined in the second convolution layer, 64. And the tunable parameters for the second convolution layer is 18,496. Please go ahead to verify the number of tunable parameters for the third convolution layer. But in total, we have trainable parameter, 56,320. Once we finish the convolution layer and pooling layer, we can flatten the network. Number of elements for this one-dimensional tensor is 4 by 4 by 64. That is 1024. We have one hidden layer and one output layer with a 10 classifier output. We can calculate the number of tunable parameter of the hidden layer. That is the input array size plus 1 bias times the number of neurons in the following layer. So I is 1024 and number of neurons in this layer is 64. Therefore, the tunable parameter is 65,600. Up to the final output layer, the input is 64 and the output is 10 there. Therefore, the tunable parameter is 650. We can check the total parameter, combine the convolution pooling and this fully connected layer is 122,570 parameters. Compared to the 9 million parameters, if you just take 32 by 32 by 3 image, flatten it, build a network. This convolutional neural network highly reduce the number of dimensions, allowed the neural network to be trained, solve the classification problem. Here are the brief introduction about convolutional neural network. The next part of this lecture, I will introduce the jet images for in-class quiz and lab. We will work on the jet classification problem for Large Hadron Collider. Here is one example. We have a top quark decay to a W boson and B quark, and W boson further decay to quark and anti-quark. This top quark can be detected by a particle field detector. This is the example of the cross-section of the CMS detector. One of the detectors discovered Higgs in 2012. If you look at this small quadrant of the cross-section of the CMS, as here, the radius of this detector is about 7 meters. It's composed of multiple detectors which can detect different types of particles. The tracker can detect charged particles. The green part is an electromagnetic calorimeter, can detect photons or the electrons. The yellow part is so-called Hadron Collider, can detect the neutrons, neutral particles, or the charged hadrons. And you can have muons, which is a minimal ionizing particle, can penetrate most of the detector and leave trajectory in a muon spectrometer. The charged particle, they move in a curve because the detector are inside a magnetic field, and you can use the curvature to detect the momentum and the sign of the charge of the particle. The top quark eventually decay to a bottom quark and the two light quark. So those quarks will be fragmented and hadronized into a string of the particles. And those particles can be detected by the calorimeter. We will use the calorimeter information to do the clustering of those particles, which can infer the original property of the quark. How can we translate the jet physics into image processing? When we have a collisions and a quark could produce a stray of the particles, and those hadrons will be detected by the detector. The detector is three-dimensional. It looks like a cylinder. We can describe the angular space of this cylinder in terms of the pseudo per rapidity eta and the azimuthal angle phi. Eta is a function of the theta, which is a polar angle. The colorful things in this detector represent the detected energy in each of the detector cell. And we can flatten this detector into the eta phi plane. And each dot here represents the energy deposition. When the top decay to 2-like quark and B quark, it could have all directions. And we can do some symmetry operation. We can rotate this energy position based on the leading energy cell and sub-leading energy cell. Furthermore, we can center the image with respect to the center of the jet. So with these operations, we can collect multiple images and superpose their energy deposition into the same plot. And if you accumulate 1,000 jets, now you can see some average distribution of the top jets. You can sort of see such a 2 light jet structure and 1 bottom jet structure here. If we try to compare to the background, which is a QCD jet, quite often it's just hadronized to 2 hadrons or multiple hadrons. Structure of these 3 subjets is not so evident in the QCD jets. In the hands-on exercise today, we'll try to practice the jet image processing to identify different types of the jets. In particular, we will try to build a convolutional neural network, and we can also practice the idea of different channels. For example, the red channel can be the transverse momentum of charged particles, and green can be the transverse momentum of neutral particles. The blue can be the charged particle multiplicities. Instead of using just one channel information, with more channel information, we have a chance to obtain a better jet classifier. Alright, enjoy your hands-on exercise today. Here are good references for you to learn more about the convolutional neural network.